In this video, we will be talking about tangential and normal components of acceleration, and then we will have one more when we will talk about Kepler's law of planetary motion. So first things first, I wanted to correct myself because I was saying that this is V, and this one is actually a Greek letter called upsilon. So I'm going to be calling it properly now. It looks like a V, but it is not. All right, so with that said, we're going to look into the motion of a particle, and we're going to look at the acceleration, split it into two components. So as it says here, tangential and normal components. I'm going to show you a diagram in a bit, but first let's play with some formulas. So if we have our upsilon equals magnitude of V, then we know that, remember from last time, our vector t, unit vector, is r prime of t over the magnitude of r prime of t, which is the same thing as v of t over magnitude of v of t. And now we can say it is v over upsilon. Which means if you look at just the first beginning of this equation and the last one, which means that we can say that v, vector v, is upsilon times t. So we will need this guy a little bit later. If you differentiate both sides of this equation, then we're going to get that a, which is derivative of v, right, is going to be equal upsilon prime t plus upsilon t prime. And then if we use the expression for the curvature that we had before, then we can say that kappa is magnitude of t prime over magnitude of r prime, oh, that's the arrow, which is magnitude of t prime over upsilon. And that means, I'm going to put it here on the side as well, that magnitude of t prime is going to be kappa upsilon, right, from this equation. Okay, moving on. Now the unit normal vector, I hope that you remember it, n, was given to us by t prime over magnitude of t prime vectors, which means that if we plug it back in here in this equation, then we're going to get that t prime is equal to magnitude of t prime n. So changing this one into here, and then instead of t prime, we're plugging in kappa upsilon, so we're going to get kappa upsilon n. Okay, so that's another thing that we need. And then our equation for a over here becomes this one. A equals upsilon prime t plus kappa upsilon squared n. This upsilon times this kappa upsilon n. So that is our equation for the acceleration. And then we can say that the first term is the tangential acceleration, and then the second one is normal, right? Because we see that this one is multiplied by t, and this one, this coefficient is multiplied by n. So we can say that, in other words, a equals a sub t, that's a coefficient, times t plus a sub n. And then from here we can see that a sub t is just upsilon prime, and then a sub n is kappa epsilon squared. So on this diagram, we can see what is happening. We can see our unit vector t, our unit vector n, right? So we're multiplying a t and then a n by those vectors, and then once we add them up, we're going to get our acceleration right here, the vector of acceleration. So another thing to notice is that the binormal vector that we discussed last time, vector b, it's not here. We don't express it. So acceleration is always going to be in the plane of vectors t and n, which, remember, we call it osculating plane. And then tangential component of acceleration is v prime, epsilon prime, sorry, tangential component of acceleration is epsilon prime, which is the rate of change of speed, and the normal component of acceleration is kappa epsilon squared, which is the curvature times the square of the speed. So if you think about a passenger in the car, that's going to make sense, because think about, you are a passenger in the car and then the driver takes a sharp turn, so it means that the value of the curvature kappa is going to be large, which means that this acceleration is going to be very large and you're going to be pressed against the car door. And then the high speed around the turn has the same effect, which means that if you're turning very fast, then the acceleration is going to be proportional. Like if you double the speed, then the acceleration multiplies by the factor of 4. So even though we have the expression for acceleration like this, it would be nice to have it in terms of r, r prime, and r double prime, because we know r, right? We know the position of our particle. So that means that we can take our dot product. I'm gonna write it here. Oh, forgot to change this again. We're going to take dot product. V is epsilon t, and we're gonna multiply it by a. Right? We're gonna multiply it by a. So let's see what happens. V dot a is gonna be epsilon t. And then instead of a, I'm plugging in this expression. So we have epsilon prime t plus kappa epsilon squared n. And then now we're going to distribute. So epsilon times epsilon prime, those are coefficients, or those are scalars. And then we have t dot t, and we have plus kappa epsilon cube, and then t dot n. Okay, now remember, t dot n, those are perpendicular. So this whole thing is going to be equal 0. T dot t is going to be equal 1, because remember, it's a unit vector. So we end up with epsilon prime, which means that now component a sub t, which is equal epsilon prime, is the same thing as v dot a over epsilon, which is the same thing as r prime of t dot r double prime of t. And remember, epsilon was the magnitude of the velocity, so magnitude of r prime of t. Now, if you should remember the formula for the curvature from the last class, when we had kappa that was given to us by the cross product of r prime and r double prime. So using that one, we can now say that the second component, a sub n, which is kappa epsilon squared, that is going to be given to us by the magnitude of r prime of t cross r double prime of t, and magnitude all over r prime of t cubed, magnitude cubed, and then arrows Those are vectors. And we're multiplying by the magnitude r prime of t squared. That's our epsilon squared. So once we simplify this, we're going to get simply r prime of t cross r double prime of t all over magnitude of r prime of t, like this. And now we're going to look at the example so that we can see what is happening. And actually, I have these two formulas printed nicely for us. So this is, yeah, a sub t. This one is a sub n. Everything that I just wrote, it's just printed in case you cannot read my handwriting. So example 7, particle moves with the position function r of t given to us. We're going to find tangential and normal components of acceleration. We need to find, so we see that we're using r prime, r double prime. So we're just going to go ahead and find those, which means that in our solution, we're going to say that r of t is now equals t squared I plus t squared j plus t cube k. R prime of t equals 2t I plus 2t j plus 3t squared k. That's easy. And then for the second derivative, r double prime of t is going to be equal to I plus 2j plus 6tk. And another thing that we will need to calculate is the magnitude of the derivative, which is going to give us 2t squared, right? 2t quantity squared plus 2t quantity squared plus 3t squared squared. And then if we simplify that, we're going to get 8t squared plus 9t to the power 4. And now all we have to do is just plug those things into our equations, and I'm going to do it on the right side. So we have a sub t is going to be equal r prime dot r double prime. So 2t times 2, that is going to be 8t plus we have 2t times 2, 2t times 2, and we're doing it twice. So 4t plus 4t, that's 8t. And then 3t squared times 6t, that is going to give us 18t to the power 3. And then we're dividing by the magnitude of r prime, which we already know is the square root of 8t squared plus 9t to the power 4. For the a sub n, we are going to find the cross product. So actually, I'm going to find the cross product here. We are finding the cross product of r prime of t cross r double prime of t, right? Which is one of the ways is to find the determinant of the matrix I, j, k, and then we're writing down our r prime 2t, 2t, 3t squared, and then r double prime is 2, 2, 6t. So then we get, we will get I times 2t times 6t, so that is 12t squared I plus, what is it, 3t squared times 2, 6t squared j plus 4t k, and then minus, we subtract now those diagonals, so k times 4t, oh, what do you know, 4t k, so those will cancel right away, and then we subtract 3t squared times 2 6t squared I minus 6t squared I, and then we subtract 6t times 2t, that is going to be 12t squared, if I'm not mistaken, j. So if we simplify this now, we're going to get 6t squared I, forgot the arrow here, minus 6t squared j. So that is our cross product, and to find now a sub n, we're going to be dividing our cross product, the magnitude of cross product, so we need to calculate square root of 6t squared plus another 6t squared, and we know that once we calculate the square root of this, it's just 6t squared, square root of 6t squared times square root of 2. Okay, so square root of 6t squared times square root of 2. So in other words, we can, I'm going to simplify it right here. So 6t squared times square root of 2. And then in the denominator, we have our magnitude of r prime, which is still square root of 8t squared plus 9t to the power 4.